it now too, because I forgot to do that. Otherwise, I'm gonna have to pull it from Twitch. Yeah, so I'm saving it. It's basically I publish them to YouTube for backup and ease of use and all that. If you ask me a question, your voice doesn't go out on the internet. And if it does, I'll make sure that it doesn't, basically. Yep, absolutely. And I guess I should ask, even though I'm concerned that I shouldn't have to. Everybody knows where the VODs are, right? Where the recordings are. Why do you always log me out right before class? If you do miss a class for whatever reason, there's these video on demand VODs. I've got all the links for each one that we've done. So YouTube, in the case where it was a Zoom lecture, I just attached the MP4. You can't see this on YouTube because your likenesses are all on that, but yeah, that is that. So, okay. Homework should make sense. You have until, what did I make it? The 5th? Yeah, so that's tomorrow. Oh, okay, good reminder. Homework's due tomorrow. For some reason, I was thinking it was due like Monday or something, but yep, don't forget to do that. That's why I'm getting so many questions. It makes sense now. All right, so let's start talking about some of the fun stuff. Blackboard says the 9th. Okay, I did extend it. Thank you. I didn't update the document. That's what it was. No, it is. Let's. This is why I don't have 30 things in 30 different places. Course information. Lab 1, February 9th. Assignments. Lab 1, February 9th. Okay. If I click it, it is due February 9th. Okay, I'm an idiot. Tuesday, February 9th. I didn't update the document. Sorry. Go with what Blackboard tells you, not with what the assignment tells you. If I remember, I'll try to update that later on, but yeah. Okay, thank you for that minor existential crisis for today. So two links I want to point out for you. The first one is actually in the PowerPoint. The second one I just added in right before class, so we don't have this. But I'll pop these into the chat for you to look around and play with. They're both really cool. Basically, what we're going to be getting to today, assuming we get through the colors and all that, is we're going to start actually talking about shaders and what they are. And these are two websites with shader-related things. So this first one, GLSL Sandbox, we talked about what GLSL is at the beginning of last lecture, right? And depending on how far we get today, we'll start digging into the syntax of GLSL and all that fun stuff. But this is your shader language. And this GLSL Sandbox and shadertoy.com, people have uploaded shader code with nifty properties and nifty examples. And the cool thing about this one is that it's actually compiling it right here. So like I could make changes to this and see what happens. All right, so here is, it's looking like ABC exclamation question mark. Color 121. Let's see what happens if I change this to 5. I don't know what any of this is going to do. Oh, there we go. Let's make this 15. Oh, it's the brightness. Cool. So basically, it's a live code editor for GLSL code that you can play with. You can hide your code if you want just the pretty effect. I don't know what this number does. Is this transparency? Maybe? Yeah, okay. But just some neat stuff if you want to play around with it. Is ShadeRed worth looking into? I don't know what ShadeRed is. Free and open source shader editor. Okay, I should know what that is. Um, so let's see. So this is an IDE for shaders, right? Um, maybe light. Okay. So this is going to be the one thing you're going to have to be careful with. So I can appreciate the desire for a good IDE. I use VS Code and it has a lot of extensions for WebGL. Just be aware that this might also be for like straight up OpenGL or Unity or Unreal shaders. Right, so if we remember from, I think a couple classes ago when we talked about WebGL a little bit, it's the embedded version of OpenGL. and it's been extended for the web, so it doesn't have all the shader features. Right? The language we're using is WebGL, or sorry, GLSL1. GLSL2 is the new one with a lot more attributes, a lot more features, but how we're using it, a lot of those things aren't supported yet. Like when we get into colors here in a little bit, we're going to talk about shading and flat versus smooth textures, and that's baked into the newer language versions, but it's not going to be there by default, right? By default, you're getting GLSL1. So just be aware when you're picking an IDE to pick the correct language version. But yeah, I mean, if it works for you, it looks kind of nice, and if it's got all the extensions you need, that's great. But on the other hand, we have, there we go. There's also the VS Code Marketplace, and there's a bunch of WebGL plugins too. So use whatever you're comfortable with, as long as it makes you productive. That's kind of the important thing, right? But I guess it looks like you get a visualizer in there, so maybe that's the good thing. Sorry, I'm not meaning to spend so much time on this. I've never seen it before. But yeah, so you have a bunch of shaders in here that you could play with, and honestly, as long as these work for WebGL um, and GLSL1, you could pretty much drop this right into one of your web pages. So you can see how complicated things are in here. So something to play around with and check out if you're looking for ideas. And the other one is shadertoy.com. Basically, similar idea. It's a portfolio of various shaders. This one looks a little bit more curated. Um, but yeah, here's some paint strokes. See if I can make this a little bit bigger. Can I touch this? No, it's just going to automatically go. But these paintbrushes have texture to them. Like you can see the valley and the different colors, and it looks like actual paint. That's kind of a neat thing. And again, shaders right here for you. So just some things to check out if you are interested in going above and beyond with shaders, which I'm going to guess a lot of you probably are, since you're in this class and you don't have a choice. Okay. One other thing I want to kind of mention too before we get too much into colors. I know somebody mentioned at the beginning of class, and I'm not trying to pick on anybody for this, but it's kind of worth mentioning from an academic perspective in a way. You go into a graphics class kind of expecting to do Unity or Unreal or the newest, latest, and greatest thing, right? And then you have the old curmudgeon like me who wants to teach you the basics, which is fine. I'm not gonna, again, it's not a, it's not hurting my feelings at all. But the stuff that you're getting in here, I think I constructed it as you're appreciating the underlying things that go on with graphics. But if you ever wanted to build your own engine, this is the kind of stuff you'd have to do. Right, if you look on YouTube, there's a ton of tutorials for building graphics engines that go into games where people don't want to use Unity or Unreal or Godot or SDL or whatever. They want their own engine because they know exactly how they're going to be drawing triangles, how they're going to be rendering everything throughout the entire process. If you write your own engine, it's very, very painful. Yeah, they translate across, but I never really mentioned the term engine because a lot of times you may find yourself actually wanting to write your own engine. And if you only know how to use a tool, you can't really write your own without a lot of extra effort. But yeah, they translate. I just kind of wanted to point out that term. There's a great YouTube series going on of a guy who used to work for, I think he used to work on Unreal, and now he's doing a code your own graphics engine, game engine series. He's out of New Zealand, I think. But good stuff. Anyway, let's talk about colors a little bit and actually talk about class-related material now. So, colors. I've kind of alluded to this along the way. We should kind of formalize what colors are in the color range and color spectrum and all that fun stuff because it's going to apply to all of these things that you're drawing to the screen. Now, if any of you have ever made a website, if you've ever done any kind of like graphics design courses or user interface courses, you probably know colors. If you've never had that though, um, Colors, we tend to think of them as a mixture of red, green, blue. Could also be hue, saturation, and lightness. That's the HSL values. Um, you can use hex code. There's that pound like FF0000 or each. Hexadecimal, like 2 hexadecimal number or a letter, hexadecimal number, will specify red or green or blue. But effectively, you're just telling your program how much red, how much green, how much blue, and how much alpha to add into the color that you're drawing. Right? So when we are specifying that clear color bit, or we're defining those vec3 for the color attributes, we're just saying how much of each are we putting into this thing, right? And I know I've kind of said this before. I just want to make sure that we formalize that because it's going to be very, very useful to basically understand very quickly how these are all put together. So again, 0 is the absence of color. They go from 0 to 255. 255 means it's full of this color. So if we said it's full of red, full of green, full of blue, it'd be white, right? Because it's got every color. If we have no color, it's going to be black. So this would be full of red right here, no green, no blue. Full of green, no red, no blue. Here in the middle, where we've got yellow, we've got red, we've got green, but we've got no blue. Basically, we're just mixing colors together, right? And we can do this in multiple ways. Now, I have a lot of background in doing web design. I used to freelance web design. I can look at ASCII color codes and probably pretty quickly understand what's going on. That's me. That's just my personal background. If this is not something that you're into, though, you're probably going to want a color code chart or a color code converter to help you along the way. And if you throw like a color code at me, I'm not going to be able to just pick it out. Oh, okay, that's that. I need this as well, so don't feel I'm not trying to talk myself up here. But let's say I want like a nice teal, for instance, and I don't really know what I want. Just going to move some sliders around, and this is the color that I want here. So let's say I'm happy with this, right? And I guess one other thing I should mention too, there are websites out there for this, but this is baked into your browser as well. If you go to your web developer tools and you inspect your page, and like you can actually find a color picker on there, or you can open up Paint, you can make a custom color. It's got these values as well. Actually, let me show you this too, because I'm gonna guess not everybody is aware of this. But I've just opened up Paint, and I could say edit colors. Here's my color chooser right here, right? Here's my red, green, blue values. If I want to use hue, saturation, I said lightness, it's luminosity. Here's those values. But again, I can define colors as necessary. I like a nice lookup table like this, but these tools are baked into pretty much all your computers. Anyway, if I wanted to draw this color, red's 47, green's 175, blue is 222, I can plug that right into WebGL. Okay, yeah, that makes perfect sense. VS Code has it too. VS Code has everything. One thing you might notice if you're looking at this, though, is that these are in whole numbers, right? So this is on the range of 0 to 255. We've been doing everything in floating points so far, right? We've been doing between 0 and 1. And you'll say, hey, isn't that a problem? Only in so much as you just need to either scale this to between 0 and 1. So you just normalize it. And you can, there's lookup tables for that out there too. I don't even know if maybe it's on here. But yeah. I guess the other thing I should mention too, I was talking about hex codes a little bit. So that's what these guys look like. Let me zoom in a little bit so you can see here. So here's black, pound 000000, white, FF, FF, FF. First FF, 255, second FF, 255, third, 255. Hopefully we all are aware that these are base 16 numbers. If you don't know hexadecimal, they range from 0 to F. It's just a conversion. FF is 255 in integer. That's all this really is saying. But if we wanted to use this in our WebGL code, like I said, you might find that to be problematic because we've been using these floating points so far, right? We can actually just use the whole numbers, it turns out. WebGL is automatically going to convert that for us. So basically, let me show you a quick example here, and I've got, again, way too many windows open. Let's look at our first gasket, since that's probably near and dear to your heart right now, since that is your homework. Let's update, do the background, or no, this is the color of the, so we're going to update the color of our gasket. So let me get out of this. Please stay full screen. Open gasket 1. Oh, I didn't add anything. Okay. It's kind of a good thing to show, honestly. I like screwing up, and you guys can all see what I'm doing wrong. So I'm going to refresh this page. Fragment shader failed to compile. The error log is constructor does not have any arguments. Okay, so we are actually seeing the error code right here. And that makes sense because I just, like a dingus, didn't actually put any values in this thing. Vec4 doesn't know how to initialize itself without any values, right? So let's say this is 255, 255, 0, 255. Right, so what I'm saying here is red, green, no blue, alpha. Save it, rerun it. It's gonna be kind of hard to see because it's yellow, right? But there's my yellow triangle. Again, WebGL does the conversion for us behind the scenes. One of the few times that you can say, oh, that's nice. Thanks, WebGL, for doing that automatically. Again, if I wanted to do this with floats, I could do that as well. Looks the same. Can add in, let's make this 0.5. So let's back off on the green a bit. And we get kind of a browny orangey color. Right, so again, I was kind of really like you all to play with some of these values as you're going to kind of understand what they're doing. It's hard to get good experience without actually playing with it, right? But hopefully that's my really short blurb on color ranges. If anybody is lost or unclear on these parameters, please let me know. I think it's fairly clear what they're doing, but I know when I think something's clear, that means everybody's probably lost. So, are we good with this? Assume we good. Yep, all set. All good in the hidden chat too. Haha. All right, cool. All right, and hopefully we remember if we want to add transparency, we add that fourth parameter, right? Red, green, blue, alpha. Value of 0 for alpha, you can't see it. It's completely transparent. Value of 255 or 1.0, fully opaque. So that's our transparency value. All right, a little bit more on the RGB color variable that we're dealing with here. You know what colors are, I've explained them to you at this point. Just to kind of give you a perspective on what they are, though, it's an 8-bit component. So you have 256 possible values. That's your standard RGB construct. Basically, it's an 8-bit integer. So 2 to the 8th is 256. In floats, we constrain it from 0 to 1, but you basically have 8 bits of information to play with. And if you're looking at it from this perspective, you start seeing a preview of the future and trying to figure out how to draw text with triangles. That's going to be a lot of fun. But yeah. One other thing here too is that these colors we're going to actually store in a lookup array, and we kind of saw a preview of that last time when I was changing colors and all that fun stuff. But if we have a lookup table for colors, it's going to save us a lot of time. So this color that you're defining, there's going to be a hidden RGB table behind the scenes in WebGL rather than do a conversion. Sorry, I'm just kind of looking off outside and it is starting to storm. It is going nuts. But if we have these lookup tables, it's going to save you a lot of memory, right? So our index, or sorry, our value that we're sending into WebGL, this 0 to 255, it's actually an index into a lookup table. So WebGL is going to maintain a lookup table of colors, and then I'm going to say 25500. It's just going to translate that to pull a value out. And kind of the only reason why I'm, kind of saying this is important for you to consider is that when you get into graphics and game design, learn to love the lookup table. Construct big arrays of things and don't you don't need to change them, but set them in memory and look up, index into those later on. It will save you so much time. I want to say it was either the original Doom or the original Quake, but they did a whole lot of pre-calculations and they just stored everything in a lookup table rather than dynamically calculate on the fly. And by doing that, you lose a little bit of memory, right? Because you're holding this thing in memory. But I don't have to do a million matrix operations. Sine, yes, thank you. The sine and cosine tables. Yes, exactly right. Trig functions. Yeah. Basically things that are always going to be the same index, right? Save yourself some computation time because you're going to need that computation time for everything else. Yep, if you are interested, look up, it's a little bit of ancient history at this point, but we used to actually have to optimize our programs. It's crazy. Yeah. So, colors. We know colors now. We know that they're indexes into tables. That's all behind the scenes, so we don't necessarily have to worry about that too much. It still works like colors as you would expect. Um, but one thing we have to kind of consider with WebGL is how it applies colors. Right, I've got this picture here. It should look pretty similar to that triangle that I created last time, right? Where I gave each vertex a different color and we had a nice like linear gradient where red was one corner, then green, then blue, and it kind of all smoothly, I'm gonna use this term again, interpolated. Basically, it's just calculating, averaging along the way. That's all that really is. But the default behavior for WebGL is smooth shading. So you're getting something that looks kind of like this when you specify vertices with different colors. And the only reason I'm kind of stressing that is this might not be what you want, right? Maybe you want a flat shade where it's like this, right? Every surface is a particular flat color, flat shade. But, your first 3D objects you're going to define, they're going to look kind of like this. Now, if we want flat shading, I've got a couple of things for you, and it's not going to be nice to hear. Well, it will be, I guess. One, by default, GLSL1, we don't really have the option to change to flat shading without duplicating a bunch of color values. So when we get into the 3D space, we have like we're going to define vertex color, vertex color, vertex color, vertex color, right? And then we're going to make triangles. It's going to be magic behind the scenes, render out this beautiful 3D piece. If we want this thing to be one color, like you see here, each of these vertices will have to be that color when we define this particular object. And then this one, right? You can actually kind of see the triangle here. In WebGL2, or sorry, I keep mixing these up, GLSL2, you have the option to specify flat versus smooth. It's actually a keyword that you put in to your objects that you're creating. We don't have that here. If you want to do that in our version, you have to do a bunch of extra calculations to make it cute, or not cute, but a little bit more optimized. If anybody is interested in that, I've got a link hiding off screen somewhere. But what you really need to know is that if you want to get to this, it's going to be something you have to do in the shader. It's not all that much extra calculation, but it's something you have to manually do if you want this. Or you just duplicate some arrays, which for a 3D object isn't that much, but again, everything we do in a little space has to scale up to a massive space. So every single optimization you can make is absolutely worthwhile. All right, so a little bit about colors and gradients and all that fun stuff. When we want to go ahead and set colors, I've given you some magic code to run, right? And we've seen how it changes color, how we can change vertex colors and all that fun stuff. Generally, you're going to set the color of your object in your fragment shader. But the thing is, when we are, let me restate that a little bit because that was kind of confusing. The fragment shader is the one setting the color. Okay, that's what I wanted to say. With this call to GL frag color equals something, right? In this case, it's going to be all red. This is what the shader is sending to the GPU. We've compiled this program, do this, right? GPU takes this GL frag color and sets that to be the color. You might remember from last time, though, we can have varying colors, right? We don't want every single vertex to be red, maybe. We want color, we want texture, we want shading, we want pretty objects. Fragment shader is still the one responsible for setting it, but you can change that in other places, which is kind of what I'm trying to get to. You can set it in the vertex shader, you can set it in the fragment shader, you can set it in the application. Basically, what we're going to be doing is we're going to pass it into the fragment shader as what's called a varying variable, and we'll get to what these little attributes mean. We could set it as a uniform variable in the vertex shader. We could set it as a vertex attribute in the vertex shader. We can set it in the application and send it to the vertex and then send it to the fragment. Basically, these terms here actually have meaning to WebGL, which, if most of you at this point are seniors, if I remember right, we know that these attributes have very specific meanings when we're defining things, right? So, this isn't a great example, but let's look at something with a little bit more color. We see varying. We see attributes. Varying. Again, these are telling WebGL that we are going to be doing different things with this. If it's uniform, it's not going to change. If it's varying, we can expect some change at some point, and we'll get to exactly what these mean. I didn't animate this in. Anybody know why this blank space is special? All right, let's pop this in one by one here. Forgot how much fun Google Slides is with their paragraph animations. All right, let's say that we're drawing our canvas, which is our background, right? It's going to be our clear color. What if we want to set, thank you. What if we want to set it to hot pink? All right, so we'll call that 0xFF, 00FF, or 255, 0, 255, or 1, 0, 1. All right, so let me do this very quickly. And while I'm doing this, my question for you all is, why is this number special? Where's my clear color at? Here we go. 1, 0, 1, 1. Because this actually does have special meaning. Is it gasket 1? Yep. There we go. Hot pink. Why do we like this one? And if that isn't clear enough, the other one we could do, make sure I've got the right one here. It's bright. It looks cool. Why do we like that color? Yes. Here's the other one. Maybe this will make it a little bit more clear. This is a little bit more common for everybody else. Missing textures in Gary's mod. It's kind of straining my eyes. What if I did that? Any guesses? Those of you that are streamers might want to look at the screen behind you. I don't have one because I'm not cool enough. Anyway, this is our key color. It's easy to key out. Thank you, yeah. So so basically this is our green screen, right? So if I am going to do a nifty Zoom session, I'm going to put myself in sunny Lake Michigan here, not already a half an inch of snow, Lake Michigan. I would put a background color behind me, and it should be different enough for me that I can just say, this color does not exist, right? We want to key it out. It's called a color key in graphics programming in the world of like video recording or all that. It's your green screen or your key color. Basically, it has to be different. And the reason why I asked you about hot pink, and pop it back, and I'll take it away here so that you all don't have to strain your eyes. Actually, let me I'll be nice here. Let's make this all white. I get a nice Red Wings logo-ish type of thing going on here. Oh, that should be red though, not pink. Say the Red Wings have been disappointing this year anyway, so. But pink, this hot pink was for a while the magic color for graphics and for video games. So if you wanted to pull down, say, characters or sprite sheets or assets that you're going to put in your game, somebody mentioned Gary's mod. This is one of those missing texture colors, right? This is the color that you key out. In languages like SDL or um, Pi, why am I spacing on the Pi game? Sorry. Basically, there is one color that you can pick, and it does not exist. Yeah, it's ugly to see in games. But basically, it's not necessarily that it's ugly, it's that it's different. You're never going to have something that is close to this color in general, unless you're going for like a pop art kind of thing. But kind of the key and why I'm spending so much time on this is that you tell your graphics program this color does not exist, ever. Yes, thank you. Fighting game sprites. So let's detour to Google Images. Old sprites, magic color. Is that going to work? Pink key. Oh God, I don't even want to go down that route. I should have known better. But basically, when I draw this, and I've said this color, oh God. When I say this color doesn't exist, the graphics engine will understand that and draw it as invisible. So you basically get a transparency here, right? So if I made, to kind of give you the effect of what I'm talking about here, let's make our Sierpinski Dealy black. Let's make our background white, just to pretend that it's invisible. Actually, you know what I can do since we have alpha? Let's just get rid of it. There. Well, now it's the pink is bleeding over, which is worse. All right, you're gonna be white. There we go. So we have an invisible background. Thank you for something that is not going to be horribly inappropriate. You're all adults at least, right? Yeah, so this would be like that color. I could go into this and key out that color, and then I would just have a sprite sheet, right? And then it would look like this. I feel like I should know this character. AVP, okay. That's where she's from. But yeah, anyway, it's different is kind of the takeaway. And if you go into any kind of video game design, you pull down stuff off of like opengameart.org or itch.io is one of the new repositories of sprites, you might see a common color like that. Nowadays, we have PNGs that support transparency, but not all of them do. And the other thing too is that older games, some of the engines never supported transparency. So you couldn't just pull in a PNG and say, this region is my walking animation, right? You also would have all that ugly pink in there. Or if it's transparent and your engine doesn't support it, it would come in as like a white or whatever your default color is going to be. So yeah, just be aware of that. What we're talking about with background, though, again, this is going to be your canvas that you're drawing to. The two things that we care about here is setting the actual color background and then calling this gl.clear. Right, so if we pop over here to the bottom in our render function, we call this every time at the start of render, that will set our background color. When we render multiple times, depending on the application, we may want to be cute about it and not redraw the whole background every time. Or, we do. Basically, this is setting your color clear. What's going to happen later on, though, is that if we call this, we're going to add some extra flags. We're going to allow for depth testing, for instance, to give pseudo 3D looks. So like here, and this is gasket 4, I'm going to OR in gl.depthBufferBit. Basically, if we want to have a 3D effect with a Z index, right? Basically, objects can be on top of other objects. We need to add in some extra bits. So this is one way that you can add some of those global flags that we talked about last time in. If we'll be getting to that, so don't worry if that's not making sense yet. Anyway, for colors, we are generally going to store them as vec3 or vec4, so you've seen this already. Nothing new here yet. If you're storing it as a vec3, it means you're throwing away the alpha value, you don't care about it. You just assume it's going to be 100% opaque. You cannot see through it. If you care about alpha, you want to do transparency, store it as a vec4, then the engine will be able to handle that for you. The WebGL will be able to handle that for you. One thing that might be helpful for you too, and this is what I did in class last time with the triangle and the different colors, create your own lookup table. So basically what we're doing here is you're creating this colors array, right? So var colors equals vec3, vec3, vec3. And I'm going to index into this later on, right? If you remember, basically I had like colors bracket 0, colors bracket 0, colors bracket 0. Don't want to spend 10 minutes digging for that since I didn't realize I was going to talk about it. But we can just index into a colors array without having to redefine this vector every single time we want to use it. Saves you time, saves the graphics processor time, and generally it's going to be better for everybody. You don't have the book, and I think it's probably in the library since I know this same book was used the last time, but you don't have to buy the book. If you're interested in this stuff, it's a pretty good reference though. But basically, if you see the slide when you're reviewing this stuff later on, you're not going to have any idea what chapter 2 is since I'm not making you buy the book. But we all remember the pipeline, right? That's basically application to shader to graphics card is basically what we're doing there. First set of the second slides. All right, this is pretty much it for this module here. So this is just kind of a little bit of a review for you to show you how WebGL kind of works together. Again, HTML is your front end. Make sure you define a canvas so that you can draw to something. Vertex shader is going to be your location information. Fragment shader is going to be your color information. We will add on significantly to that. These are compiled bits of code, which sounds very bizarre to say in a HTML world. You don't compile HTML, but these get compiled by the WebGL engine. JavaScript is going to be your application file. This is where basically you tell it how to talk to the shaders, what data to send to the shaders, and then the shaders are going to package that up and send it to the graphics card. For instance, let's do a little bit more of an advanced example here. So I might have in a variable hook, right? We've got that V position, V color. We've defined those and we've pulled them in our application code. And I've just said you just do this and it'll become apparent as we go. But what if we wanted to update our shaders? Now, this is something where we're going to animate things, right? So if I pop over here to chapter 3, and it's rotating square 1 is the one I want, you get something like this, right? So actual animations happening here. And those enterprising individuals that were lost on my explanation of the homework assignment might see, hey, this thing actually looks like it's rotating. I wonder if there's any magic to that. And I'd say, you're right, there is magic to it here. But if we look at its code here, rotating square 1, we're going to, I just want to take a quick aside because I think this is going to be helpful to maybe illustrate some of these concepts I'm talking about. One thing which is going to help you mentally with how this all links up is that the shaders are not the first thing that happens, right? The application happens first. So your HTML is going to load. It's going to see the shader code and compile it, but the JavaScript application is going to be the first thing that runs. That application is going to execute, right? So the JavaScript files, this is going to run once our window loads, initialize WebGL, do all this fun stuff. And then these magic lines of code I keep talking about here, where we're setting our buffers, this is where the application talks to the shader and sends it out, right? And then when we get to render, this gl.draw arrays is basically telling the shader, we are ready to go to the GPU. Do this, right? whatever we have in our buffers, where again, these buffers are effectively global variables because we're linking them all together all over the place, draw whatever is in there. So why I'm talking about this right here is that we can actually have a shader do something interesting, right? So in this example, we've got a rotating square, right? It's rotating based on my mouse position, so we've got some nifty little interactions with our browser. Basically, it's picking up the mouse cursor. But in here, we have some extra stuff going on. So our fragment shader, still boring. It's a pass-through shader, not doing anything. But our vertex shader is actually doing something for once. So we have our V position. This is not new, but we have this uniform float theta. And then we're doing stuff with this theta, right? So we're getting the sine and the cosine of it. And then rather than just doing a pass-through sending like our GL position equals V position, we're actually setting the X, Y, Z, W parameters of that variable. We didn't know those parameters existed until now, right? But there's actually very specific attributes for these variables. I want to set the X, I want to set the Y, I'm going to set the Z, I'm going to set the W, which is something we'll talk about further on down the line. It's got more to do with like camera type stuff. But what's this theta? You don't see it in here, right? It's we're defining it. Is it always 4:45 that's the children start being unhappy? I just don't like being cooped up while I'm teaching. Okay, so we have this theta. And I'm just kind of, again, skipping ahead a little bit to show you what we're doing here. But I'm defining theta starting at 0.0. We have our basic WebGL program. Again, nothing too exciting. Set up WebGL, set up the canvas, set up our viewport, set our clear color, initialize everything, vertices, nothing crazy yet. We're even going to do our basic GPU loading, right? Associate vertices with our buffer, associate V position with our application. Nothing has changed in these lines as well. But we do have a slight difference. We have this theta loc, and the loc is local here. GL.get uniform location. So we're going to link a variable up to our shader, right? So we're not just using the defaults here, we've actually defined a new one. Let's link them together. Basically, we're telling the vertex shader that this is going to change. We're sending you values, right? In this theta, I thought it was tied to my mouse. Oh, you know what's interesting? Hmm. Yeah, mildly confused. I think I've got a conundrum here. Why are you doing that? Sorry, I'm mildly puzzled because I'm just realizing. What? I think this might be a browser thing going on here. No messages, no warnings. You all see it going faster, right? I'm not like having a stroke. Huh? There is one that deals with the mouse, but it's not this one. When I was playing with it, I was going to talk about it because I could have swore the mouse was in here, but my browser is very haunted. This is a cursed stream. Mail this to 7 of your friends to stay alive. Okay. I'm gonna have to look into that later because I don't have an explanation. The only thing I can think of is that my frames per second changes for some reason with mouse movements in here because I've got stuff where we dink around with the mouse and it changes the application, but this one ain't it. Anyway, let's just assume it's going at a reasonable speed. All right, cursor come back. I thought my little cursor highlighter was doing something because it's an auto hotkey script. Anyway, what's going on here is that every single loop of our animation, yeah, it's constant. If I'm over it, it's doing stuff. If I'm, oh, now it's okay. So if I just stay here, it's gonna do it too. All right. Yeah, okay, so now I'm a little bit better. We're not locking the frames per second. So probably what's happening here is that the combination of all the stuff I'm running on my computer in addition to WebGL, it's probably bogging down my browser a little bit. I bet, just for fun, because it's always fun to see things go wrong, right? What does my performance look like? How much you want to bet that I'm getting like memory spikes in Chrome or something like that? Yeah, that's probably what's happening. Anyway, live debugging, right? Live coding is the best way to learn, right? Anyway, back to where we were. We have this theta variable. Theta we have linked to our vertex shader. In our render function, we're going to call it once. We're going to clear our screen. We're going to increment theta, and then we're going to call gl.uniform1f. And basically what we're doing is we are saying whatever was in theta, put into theta loc. Theta loc is associated with our shader. Draw that as a triangle strip. And again, if you remember from last time, we used triangle strip to draw a easy square. And then, as if I recall, Philip had this right, because I'm going to guess you've got some JavaScript experience. Window.requestAnimFrame. This is going to recursively call render. The smart way to do this would be to lock this to a particular frames per second, right? Only allow requestAnimFrame to be called every so often. We don't have that in here. That's why we see this odd behavior. It's going to be my guess. But we have a variable that is rotating an object that we are sending from the application. What does this mean to you, and why am I wasting so much time talking about it? You might say. And I'd say, well, I had nothing better to talk about. No, it's actually relevant. By doing this, theta plus equals 0.1, go back to your vertex shader, we're doing some math, right? Sine and cosine. We are updating our x and y positions of our vertices based on a calculation. This is where a knowledge of trig math is going to be very, very helpful for you. Because when you start moving things around, they're all going to be related to these mathematical identities and functions that you learned back in high school, maybe a little bit in college as well. But if you want to spin something around a circle, there's a math function for that, right? If you want to translate something from here to here, we don't necessarily want to say, okay, move from 0, 0 to 5, 5. We want to do the linear function to move there. We want to calculate. We don't want to set vertices directly. So we have a mathematical function to handle that for us. And again, the GPU is great at these kinds of calculations. That's why it turned out to be really, really good for matrix math, which is why all the Bitcoin miners bought it up, because that was doing a ton of matrix math. But nice little example for you, a little preview into your future for what we're going to be getting to. Yeah, frames per second, that's all that is. Okay, questions. Oops, getting ahead of myself in the wrong set of slides here. Questions at all on our full program? I'm not going to go over this last one here again, but just make sure that if you are writing your application that you bind it inside of an onload command. Because again, you want your script to exist when the canvas exists as well. So just put your main function, your main code in there. But we good with the basics, colors, program structure, a full program, things of that nature. Hopefully you can take what you got in here and extend it to more complicated things. Kinda, sorta, maybe. Is there anything unclear? Because if it's unclear to you, there's probably something unclear to other people. Otherwise, I will get set with the next bits. So we got about 15 minutes left. The only thing that's unclear right now is your camera. Yeah, I've got this, it's from the department. They're Microsoft HD cameras that does this weird like autofocusing thing every so often. Let's be honest, you don't want me to be in focus. It's a horrifying sight, full of despair and glaring. Exactly. Okay, today and next time, we're going to talk about shaders. So we're going to kick it off here a little bit. Shaders are the exciting things in graphics right now, right? One of you asked me, are we going to talk about shaders soon? And I said, yes, we already did. And probably the reason why is that this is the buzzword that you hear when you hear shader, right? So let me give you an example here. Minecraft's a great one. Here's our standard default Minecraft world, and something I keep forgetting to get into, but got a shout out to the GVSU Minecraft server that is it Mr. W on Discord runs. I was trying to remember what his Discord name was, but you slap a shader on there, and all of a sudden it's pretty, right? It's something that is going to modify your graphics, and that's why we have all kind of heard of shaders as this kind of magical thing that just fixes all your problems. And what we're learning in here now is that shaders are just functions that we're calling. They talk directly to the graphics card typically, right? But they're just extra functions. Go back to that explain Minecraft's acid shaders. Is this something safe for work for me to look up? The problem I have with Minecraft is that I have a great time with it, and then I die like somewhere far, far away from my base, and I lose all desire to go back and start over. Minecraft, Mincecraft, Acid, Shader. Are these the pretty ones? Oh, wow. Okay. I see why they're acid. Yeah, absolutely. There's no difference to this than to any of the other shaders that are out there. Let's make this bigger. Hey, finally remembered to just do that. All right, so I assume we're doing some kind of a warping. So it looks like you're kind of on acid. You've got a what was that movie with the world turning in on itself? God, I swear, the more I get older, the less I can quickly remember things like that. Um, Trippy. Inception, thank you. My mind kept getting stuck on the Departed. It's another DiCaprio movie. Anyway, yeah, they're just toying around with the vertex location here would be my guess. Right? So I'm sure they're just applying mathematical transforms to the world so that you stretch and pull things in multiple directions. That's probably all that's going on here. So I mean, if you're looking at this, and I've never played it, I don't know how in-depth crazy this thing is. Maybe it does lots of warping because you're on acid playing this. But my guess is it's really just playing with vertex locations based on some kind of a mathematical function. It looks cool though. Yeah, they shift as you move. Okay. Might be worth checking out. That looks like fun. Looks like it would be vomit inducing too. But yeah, I mean, if you're looking at that, just kind of consider that maybe we're not playing with the quality of the textures or anything like that. You could just be playing with the vertex location of all these voxels that they've got. Right? So these are all just 3D cubes, and we know that a cube is basically just a bunch of triangles linked up together, right? So just start shifting vertices all over the place. Can you guys hear that? God, my near 2-year-old has discovered his temper. It's hilarious at times. Absolutely. Let's see, so last semester I had a 10 o'clock class, and at 10:45 it was always like, or 10:30, 10:45 was snack time. And that was when I think that class probably heard them scream every single week. I mean, to me, you all sound like that anyway, right? Just kidding. No. Anyway, shaders. Enough of that fun stuff. So we can basically play with absolutely. Oh, this is going off the rails quickly. I love it. Some more fun classes. So shaders, vertices, and fragments, right? So that acid, yeah, way to keep me on topic there, everybody. If we keep them off topic for 15 more minutes, we don't have to learn anything new, right? Um, so that acid shader is a great example of playing with the vertices and the locations of things. Minecraft being open source, I'm sure you have access to that data, right? You probably have access to the dictionary of objects that exists, or the pool, or however they represent all of that stuff. Um, Vertex, you can morph things, you can transform them, you can play with shapes, make them a little bit more continuous looking instead of blocky if you wanted to. Or you can play with the lighting, make it that nice cartoon, that toon shading where everything's kind of flat yet slightly continuous looking. Maybe give it a nice little HDR effect. But this is our fragment shader. Vertex shader could be that acid trip thing. Absolutely. But that's all shaders are doing. And the cool things about shaders is that you can basically overlap them or intertwine them. Um, he gets very upset. Um, I could apply an HD shader. I could also apply an acid warping shader. I could basically just keep building upon shaders if I wanted to. And that might be a good case for where you load them in outside your program to keep everything nice and clean. But there's nothing stopping you from doing multiple shaders. It's again all being really offloaded to the GPU. The thing to keep in mind with shaders is that all you're really doing is a whole bunch of matrix math at the end of the day when you compile your program and it gets linked up to your GPU. If I want to transform vertex coordinates, I'm doing matrix multiplication or I'm doing transposition, right? All these horrible terms that if you're not a matrix math person, you probably hate and are afraid of and despise in all the same breath. Not that I have any personal experience with that, but that's all you're doing is just transforming matrices. We're also going to do that with our camera. If you want your camera to be swinging around your character or giving you like a perspective of the world around you, you're just transforming matrices and you're doing that probably in the shader. As long as you want your program to be performant. So that's what our shaders really are. Again, there's not a lot of magic behind them. It's a slightly different language. It's C-like again, but it's just matrix math. It's really not that crazy. So here I've got two of these teapots. I've got one where we're actually doing something that we haven't talked about yet, but lighting. This one is calculating light and what light looks like on this object on each vertex. This one is doing it on each fragment. You can kind of see the difference, right? Here we have a smudgy, blurry light, and here we have kind of a point reflection, like if you had a light bulb bouncing off a shiny surface. While we're here, and again, this isn't really to show you, okay, if we do vertex, it's going to be this. If we do fragment, it's going to be this. Mainly to show you that you can do different things with your shaders, right? Maybe this is optimal for your project. Maybe this is optimal. Calculate it wherever you want. But while we're here, does anybody know why you keep seeing these teapots? If you've ever looked into graphics at all, you've probably seen these teapots. If you've ever looked into an OpenGL resource or any kind of 3D modeling resource, you probably have seen this teapot. What is so cool about these teapots? Other than their teapots. Yes, does the question make sense? Yeah, so they're simple but complex. Exactly. Basically, the little bit of backstory here is that one of the people who was, yep, I can't remember if he was developing OpenGL or an OpenGL textbook. It escapes me now. But basically, he had this teapot in his office, and he was looking at ways to prove out, an application for graphics. And it is a very simple looking object to model, right? You have handle, you have this the little cap, you have the spout, but it's pretty complicated to model. We talked about triangularization and tessellation before I've thrown those terms out. How do you transform this into a bunch of triangles? We'll get to the actual algorithms for that later on, but you have like this curved surface, you have the shadows, like you said, maybe different textures and surface types. But this is actually pretty tricky to model from a algorithmic perspective. Right? If you wanted to set all the vertices by hand, that's fine, you could do that. But figuring out exactly how to model this with a program is actually tricky, which is why it's used to kind of like prove out graphics algorithms. And because it was the first one, it basically stuck, and we just keep modeling this thing. All right, I showed you this figure before too, right? We've got our shading, our mappings that we can do. This is, I think, day one. Smooth texture, shiny texture with environment mapped onto it, applying bumps and, kind of different specularities and things of that nature to our object. But we see a lot of different results, right? Utah teapots. 3D test model that has become the standard and an in-joke. Yes, there you go. But the point is it's kind of a complicated model, even if it doesn't look complicated, right? Yeah, in-joke, or we just keep using it because it's fun. But yeah, thank you for that. Need a Wikipedia bot in the stream to help out, I think. I know there are bots for that in Discord at least. It's got to be one for Twitch, right? Fact check your professor live. Sure, everybody would love that. But what are we actually doing here? We're taking our shaders and we're mapping a texture onto our objects, right? Let's say that we actually have a algorithm for defining, this teapot here, right? We go through the long and arduous process of triangularizing it, so figure out where all the vertices are that make up this mesh, and now we're going to put fragments down onto it. Is it going to be smooth, right? We don't have any color, we don't have any texture, it's just a raw object. Or are we going to make it shiny? We have to represent that with our GL frag color and our textures that we'll get to later on. But the interesting thing that you see here, I just kind of want to highlight this a little bit. You're taking these surroundings and mapping it onto the surface, right? This ball does not actually reflect anything because it's just a computer generated object. We give it the illusion that it's reflecting things based on the vertices and the fragments of the things around it. You could do this with like ray casting. We talked about that a while back, where you bounce the light off and see what reflects. That's one way you could map these objects onto the screen here. So basically, our shaders are going to handle all of this type of stuff. That's kind of what I'm getting at. Let's see. Talk about a couple more things and then we'll call it a day, I think. So just to kind of give you a little bit of a history on shaders. They used to be kind of assembly-like, so be very happy that you have a C-level language to work with because nobody likes assembly anymore, unless you're a masochist. He said, being somebody who likes assembly. Um, Basically, they started at assembly-like. OpenGL comes, adds extensions for shaders. So OpenGL did not start with shaders. OpenGL started with raw CPU processing. Shaders were added on later, basically as extensions to the language. Um, there's also something called CG, or C for graphics. It's a C-like language, also feasible. Basically, the nice thing about shaders is that they're transferable, though. You write a shader, it's going to work with OpenGL or work with DirectX. If you scale it back a little bit, it will work with WebGL. You're probably all aware. If you're not, Unity, Unreal Engine, they all support shaders. You can import them into those engines. Now, the actual import process may be different engine to engine, but by and large, the shaders will work with them. And that's how we get these very powerful environments and games that you're seeing. They're all shader based. And this leads us to GLSL, which is something that I introduced you to already. Um, this is the language that you're writing in your HTML pages for the Vertex and Fragment shaders. This is your OpenGL shading language, and it's something that we're going to be using to, handle our shader code. All right. Hopefully we're good so far. So one thing about OpenGL shading language, or GLSL, it started with OpenGL 2. Once you hit 3.1, shaders are a necessary part of it. They're required, so we're going to take care of our graphics processor and make our life a lot easier from a programming perspective. But the kind of the neat thing that you really are going to take from this is that we have, oh my God, I might just end the stream because this is sounds like my help is needed. I guess let's do this since I'm just going to pretty much end here anyway. Does anybody have any questions from today? Everything making sense, hopefully. Basically, what we're going to be getting into next time is the actual nuts and bolts of GLSL, what varying means, what attribute means, what uniform means. I introduced uniform in terms of theta. We're going to be using uniform in a very specific way. So, all good here? Okay. If you came onto the dumpster fire at the beginning of class, homework is due February 9th. I misspoke. So you guys have basically a full, not a full week, couple, 5 days. But get it started early if you haven't looked at it. Um, that way I can help you if you have any questions crop up along the way. So other than that, I hope you all have a wonderful day. I will see you on Tuesday. And yeah, have a great weekend. Enjoy the snow. Get out there and play before it gets too cold, I suppose. I know I will be doing that hopefully tomorrow. All right. Bye, everybody. See you Tuesday.